Let's look now at section 14.2, double integrals and volume. Now, in Cal 1, we developed the idea of area under a curve by taking a planar region and then breaking it up into small little rectangles. Now, of course, in Cal 2, we see that that's not necessarily the way you have to do it. You could always approximate with trapezoids, or Simpson's rule shows you can even do it with something with a parabolic top. But in Cal 1, you keep things simple. And you say, okay, I can approximate this area by using a bunch of little rectangles. All right, very nice. And in fact, we have an approximation. That's the Riemann sum. So here we say the area underneath this curve is given by approximately the sum of the areas of these rectangles. And we see that as the sum as I goes from 1 up to n of f of x sub I comma delta x sub I. Where here you're just saying, okay, there's the base of my rectangle, and there's the height of my rectangle. Now the bases are small, so we give a little tiny change in the direction of x. The height is simply given by this upper function. Here's your f of x. And so if you plug in different points along the x-axis, that gives you different heights straight up and down. So base times height gives you the area of a rectangle. And if you add those together, you get approximately the value of the area, more or less. Now, of course, the big punchline is that the limit operation allows you to take this approximation and make it better. In fact, it allows you to make it so good that this approximation becomes precise. The error between this approximation and the actual area goes to 0. So here we say by passing through the limit, we no longer approximate, but now it's exactly equal to. And this is the limit as, and there was a couple of ways of writing it. You could say the limit as n approaches infinity. You have the number of rectangles goes on to infinity. Or you could say the norm of your partition approaches 0. How wide these are all goes to 0. Either one means the same thing. If you take the limit of the sum as I goes from 1 up to n of f of x sub I delta x sub I, that's exactly your area. And we have a notation for this, of course. That is our definite integral. Here we can evaluate this as the integral from a up to b, where again a and b are just the boundaries along the x-axis, which tell you your area starts from here and ends here. Your rectangles start here and end here. That's the integral from a to b of f of x dx. All right? And that's how we define our area back in Cal 1. Well, now we're dealing with functions of higher variables. So let's consider not a function of x, but a function of x and y. Well, we've seen in previous chapters that a function of x and y is going to be in 3 dimensions. Something like this. Here's our x-axis, our y-axis, and our z-axis. And I'm labeling the positive directions. That's positive x, positive y, and positive z. All right? So now I'm going to take this coordinate system, and on it, I'm going to go ahead and lay a surface. I'm going to go ahead and lay a surface over a region. Well, you know what? It might be a good idea to define my region first. So here's the domain of my function. And I'll call this the region R. Just like I'm usually calling regions on the plane R, I'm going to go ahead and keep that convention. So now here's my domain, and I have a surface that lives over this domain. So here I'm going to draw something that I know how to draw. I'm going to draw a little dome. And it's okay if this surface lives beyond this domain, but we're going to focus on it on just this region, or just over this region. All right, so that is our surface. Well, now it becomes apparent that if I'm in 2 dimensions, I can look for area, but in 3 dimensions, area doesn't really cover it, because area would only talk about the stuff down here. It would only talk about what happens on the xy plane. If we want to extend into 3 dimensions, we need a length and a width, just like we have here. but we also need to talk about height. And if we talk about length, width, and height, that's no longer area. Now we're talking about volume. All right? So how do we express this volume? Well, we're going to use the same idea. We're going to break this up into little rectangles. And you say, well, yeah, but rectangles are flat. This is 3D. Okay, fine. Instead of rectangles, we're going to break this up into little boxes, as in three-dimensional boxes. The proper name is parallelepiped. Okay, little boxes, because that's a mouthful to say. But here, let's go ahead and actually formally state that a parallelepiped that's basically a 3D box. And although they can take any dimension, what we're going to want is we're going to want ones that are tall and skinny. So here, instead of having a rectangle inside of a plane, I'm going to have a little parallelepiped. I'm going to have a little box that has length, width, and height. And there we go. So we have a little box. So now the area of a little box is easy to find. The volume of a parallelepiped is simply given by its length times its width times its height. Volume of parallelepiped, length times width times height. Okay, well, here I have my length and my width are just along the x and the y axis. Notice, length and width are the base. So here that's going to be, oh, well, that's just a little tiny area of my base. Just like over here I had a little tiny interval, here I have a little tiny area. So this thing right here is just a little small area. And so I'm going to call it, reminiscent to this, I'm going to call it delta A. Change in the area, not change in the x value. Now here, there's going to be different ones. I'm going to have one box here and one over here and one over here. Okay, so here I'm going to index them A sub I. That way there's, this is my first one, and then my second one, my third one, fourth one, fifth one, and so forth. The height, well, that's nice and simple. I just plug something into my function, and that'll tell me how far up I go. So here, that's going to be, oh, well, that surface is given by a function of two variables. Here, z is equal to f of x comma y. So while this is my little area, this right here is the height of my rectangle, which is an f of x comma y. Well, again, there's going to be different ones. There's one here, but there's going to be one for this rectangle and one for this rectangle, and so forth and so on. So here I'm going to go ahead and index them. That's f of xi, yi, for that one in particular. Okay, so that's the volume of a parallelepiped. Okay, cool. So now what? Well, that's only one. But if I take a bunch of them and add them together, I get something like this. So if I take several of them and I start adding them together and I start stacking them together, I start getting a bunch of boxes that fill in the space inside my region. I end up with a bunch of little boxes. Okay, so to approximate this volume, the volume underneath the solid, the volume under the surface, now here's a solid region, I'm filling it in, is approximately equal to, well, I'm adding these together. So I'm going to take the sum. Now, I don't know how many I have, so I'm just going to say from I equals 1 to n. This is starting to sound familiar. I have the sum as I goes from 1 to n of, well, that's a height times a base. Yeah, that's starting to sound familiar. It's the sum of a height and a base. Before, your base was one-dimensional. Now your base is two-dimensional. But so what? It's still base times height. So this is going to be f of x sub I comma y sub I. And here you have your delta A sub I. And that approximation is just an approximation. But you know, if I make these boxes really, really small, really, really thin, and really, really skinny, then I can fit more of them together. And as we've seen before, the more boxes you use to approximate your expression, the better the to approximate your solid, the better the approximation becomes. So what I can do here is I can pass through the limit, and now instead of saying that my volume is approximately equal to that, I can say that if I take the limit as n approaches infinity, or likewise I can say the norm of my partition approaches 0. Now you might say, well, over here I know what the norm of my partition is. The norm of my partition is how wide these are. So those are going to 0. What do I mean by the norm of the partition going to 0 here? Oh, that just means that these little areas are dropping to 0. You say, well, how do you measure that? There's a few ways you can do it, but the simplest way to visualize it is just to say, well, look, these are little rectangles that act as our base. If I make one of these really, really thin, but let it stay wide, let me just go ahead and draw that out. If I have this object that's the base of this solid, if I let it get really, really thin, but it's still wide, that's not exactly what I'm going for. I'm trying to make everything come down to a single point. That way I have at each point, I have a different box. Likewise, this wouldn't work either. I wouldn't want this to stay tall, even if it got skinny. What I want to do is I want to condense this down to a single point. I want this to come back this way, this way, this way, this way. So one good way to think about it is the norm of the partition just tells you the distance across the diagonal here. All right, I want the distance across the diagonal here. The distance across the diagonal is staying pretty big. But if I make them if I make both directions shrink down, both length and width, the distance across this diagonal is going to 0. All right, so that's what we mean by the norm of the partition. There's a few ways to define it, but for us, just visualize it as how far across it is diagonally across one of these little squares. If all of those diagonals go to 0 in size, that's what we're after. We're trying to get these little boxes to condense down to a single point. All right, so that's the limit as n approaches infinity. The norm of our partition approaches 0. The sum as I goes from 1 up to n of f of x sub I, comma y sub I, delta a sub I. And we're going to go ahead and borrow the notation that we used back in Cal 1. This is the limit of the sum of a base times a height, just like we had up here. So we're going to borrow this notation and write it as an integral. This is written as the integral. Now this is going to look a little strange at first, but we're going to have some nice conventions to help us simplify this out in a bit. But our definition does look just a little different than what you might be used to. This is called the double integral over the region R. And you say double integral. You mean like iterated integral like before? Kind of. There is a strong connection between the two. But here this is called a double integral. It is related to the iterated integral as we'll see in just a bit. But this is called a double integral. R just tells you, oh, that's your domain. It's like saying, oh, I have the integral from A to B. Instead of describing the region by saying, oh, it's the circle of radius 5 that's centered at 1, 3. No, we're just going to say over the region R. So that's a double integral over the region R of our function. Now note that's a function of two variables now. And here, this is, delta x becomes the differential dx as you pass through the limit. So here, delta a will become the differential dA as you pass through the limit. This right here, we'll have a few different ways of expressing this, and we'll have ways of changing it into other expressions in later sections. Eventually, we'll come to what's called the Jacobian, which we'll talk about that later. So all of this brings us to some definitions here. All right, so the first one, let f be a function that is defined on a closed and bounded region R. That R is in the xy plane. The double integral of f over R is given by, well, this notation. This is read as the double integral over R of f is equal to this limit. And of course, that is exactly what we build over here. So this is simply formalized in this definition. We also see that if you're looking at this definition, One way of interpreting that is as the area underneath this surface down to this region on the xy plane. That is formalized by this statement. Let f of x comma y be an integrable function. In other words, we'll be able to take the integral here. The integrable function over the plane region R in the xy plane, such that f of x is greater than 0. Here we want everything to be positive. Once things are negative, then we have to worry about the difference between integrals and area, where integrals can be negative and area cannot. So here we're going to restrict this to being strictly positive. So here you have a surface that is entirely over the xy plane, nothing underneath. If that's the case, the volume of the solid region above R and below F is given by that double integral. And that's simply formalizing this illustration here. The volume between this surface and this region can be thought of as this double integral. And that's what this says. All right, now, once we define the double integral, we can state a few properties of the double integral. Now, thankfully, notice that our double integral is defined the same way that our normal integral was. Here, it's the limit of a sum of these two products, or of the product of these two factors, rather. And same thing over here. This is the limit of the sum of the product of these two factors. Yeah, visually, geometrically, they're different, but they're derived very much the same way. And as such, it stands to reason that a lot of the properties that you had for regular integrals should continue to exist for double integrals. And in fact, you see a collection of them here. If we begin with f of x and g of x as functions that are continuous over a closed bounded region of R in the xy plane, here let's start off, let's let c be a constant, it's just a regular number. Then the following things are true. If you take a double integral of a constant times a function, that's the same as taking the double integral of the function and then afterwards multiplying by the constant. Or, as some people like to say it, you take the constant and pull it out. That was true for single integrals, and that's going to be true for double integrals. This one says, if you take the double integral of the sum or difference of two functions, that's the same as taking the integral of one function, taking the double integral of the other function, and then just adding or subtracting after the fact. Or, some people like to say, you can split the integral. You can take the integral of the first, integral of the second, and then add or subtract. Putting these together, this is called the linearity property. Of double integrals. Going back all the way to Cal 1 through Cal 2 and even in the beginning of Cal 3, we've heard this phrase over and over again. Linearity is one thing that we love because it makes a lot of computations simple. We can separate things out into smaller component pieces. The derivative is a linear operation, the integral is a linear operation, and now the double integral is also a linear operation, which is going to make things very, very nice to compute. The next one, this one says that if you take the double integral of a function, if that function is strictly positive, then that integral must also be positive. That interpretation of that one can be done geometrically. Right? You can think of this as saying, okay, well, look, I am taking a double integral. Well, the double integral is defined as this limit. But one interpretation, one way you can think about the double integral is it represents the volume of a solid, the volume of the space underneath a surface. Right? That's not the definition. That's the definition. But this gives us a nice intuition. With this intuition, we can say, well, f of x is greater than 0. Okay, well, that means that all of the z values, remember, this means z is equal to a function of x and y. That means that we have some surface over the xy plane. Just like that. Oh, okay, so then I'm finding the double integral of that function over a region. Okay, so that's just using this idea here, that that's the volume of a solid. then this double integral is nothing more than the area underneath this surface down to this region. Okay, so as long as this is positive, then this is just an area. Oh, but areas have to be positive, right? The smallest area can be a 0. You don't have negative area. Okay, so then if this is positive, then this thing is representing a volume, which means it can't be negative. So it must be either positive or, worst case scenario, it must be 0. This one can also be interpreted geometrically. Here you have two functions, f and g, and the relationship between f and g is that the f of x comma y will always be at least as big as g of x comma y. Might be bigger, but it's greater than or equal to. So at the very least it's equal to, but usually it'll be greater than. Okay, so if you can visualize that with the same kind of illustration, we look at this and say, okay, I have a function f of x, and that'll be some kind of dome up here. Let's do that. All right, and that'll be my f of x, comma y. And now let's go ahead and take a function g, and we notice that g must be lower than that. Okay, so then maybe at some point it'll actually touch f of x. Maybe these two surfaces will coincide; they'll be equal. But if they don't coincide, here I'll make them touch at that point. If they don't coincide, well then g is lower. Okay. So now remember, these by our previous result here can be thought of as a volume. Okay, so this is the volume underneath that surface f, and this is the volume underneath that surface g. So here, if I find the volume under g, and if I find the volume under f, well, clearly f is higher up, which means it'll have more volume underneath it. So here, if f is higher, then the area under f must also be higher. Note that none of these are formal proofs. The formal proofs of these would require a lot more detail, but this is sufficient to understand what the properties are saying. All right? The formal proofs of this would be covered in a class of analysis. Analysis being, for lack of a better term, it's like you're in Calculus 3 right now. It would be like Calculus 5 or 6. If you follow this track higher up, eventually you get to things that are a little more theoretical, and some of these properties and theorems are proven there. We will still certainly prove a few things, and we'll definitely motivate as many things as possible. But some of the proofs in this course are a little beyond what we can do right now, so we'll do what we can. All right. So that's this illustration. And finally, this last one says, okay, let's say I wanted to find the double integral over r of f. Okay, let me draw that out. Again, this is nothing formal in any way, shape, or form, but it does help you understand what the notation says. It does help you say what this says, even if it doesn't exactly tell you why it's true. Okay, so I have a region. I'll call that R. And I have some surface that is over that region, something like this. What this is saying is I can split this. I don't have to treat R as a single region. If I want, I can split it apart. I can treat this as R1, and I can treat this one as R2. As long as these don't overlap, notice there's a clear distinction between the two. There is no overlap. As long as they don't overlap, and when you put them back together, they give you back the region R, their union is R, it doesn't matter if you take the integral all at once, or if you want, you can take the integral in two separate stages. And you could say, okay, let me find this integral over here first. Let me find the area underneath here. And then separately, let me find the area over here. I keep saying area. There should be volume. We're in 3 dimensions, yeah? And you note that if I find them separately, put them back together, that does give me the total volume of that solid. Or in other words, here you can think of this as, oh, well, if I have a double integral of a function over R, I can go ahead and split that into two pieces. And as long as these two bases don't overlap, these two solids will fit together to form my total solid overall. And that's an illustration of this. But now the question remains, okay, so you have motivated a definition, and we went ahead and formally stated the definition, one application of that definition, and some properties of that definition. Okay, but how do we do this? How do we compute this? Well, let's take a look here. I mentioned something about a double integral earlier. Consider the following illustration. And the nice thing about videos and being on paper is that my drawings can actually look a little more decent than usual. Whiteboards are hard to draw on. All right, so if we look at this, consider the following solid region. Okay, so here I have like a rectangular prism. The shaded area in gray is the region R. It's on the XY plane. So here this R represents this flat plane that's laying down on the XY plane. Here I have a surface that's off the XY plane, and I'm calling it f of x comma y. And it's this sort of slanted plane right here. There's nothing special about a plane except it'll make the drawing a little easier to follow. This could have been any shape, could have been any surface of any shape, parabolic, hyperbolic. It wouldn't have mattered. All right, now the nice thing about our previous definitions and how we motivate and connect them is that, okay, here I can think of this double integral as being the volume inside of this solid prism. Okay, so what? Well, remember, if we're thinking about a volume, we can break that apart into individual little pieces. You say, what do you mean? Well, thinking back to how we develop area in the first place, we slice it up into little tiny strips. Same thing for volume. If you were going to find this volume, you don't have to find it all at once. You could find the volume of a tiny little strip. So let's say I took a really, really fine knife and I just sliced right along here. And I just got a really, really, really thin slice back there. The one that's all the way to the back. Well, that really, really thin slice would just be a triangle. Okay, cool. Oh, but I know how to find the area of a triangle. And you say, well, yeah, base times height divided by 2. Well, yeah, that's true. But let's do it the calculus way, because that's what we're trying to generalize here. So here, this volume of this triangle, and of course, it doesn't have to be a triangle. It could be any shape. Here, the volume of just this one strip would be, this is the volume. Now remember, we sliced this infinitely thin. This is flat. This is the volume of a very thin strip. Okay. Well, if that's the volume of a very thin strip, that's basically just area now. So this would be, oh, well, let's see. If this is the volume of a very thin strip, this is the area of that strip. Okay, so we're back in 2D. Oh, but I know how to do that. I know how to find the area of a flat surface. I know how to find the area of a flat region on the XY plane, or in this case, I suppose it should be the YZ plane, but whatever. And that would just be the integral from A to B, the integral from A to B, of this right here, from the upper surface down to the lower surface. Okay, so that would be given to me by my function, f of, now of course here we're only dealing with y and z, so x is a constant here, right? Notice we're not moving along the x direction, x is a constant. Oh, well, that's fine. That means that x can't be the variable of integration. Well, there's only one other variable that I could use, and that's y. So that would be dy. Okay, cool. So the volume of that thin little strip would be something like this. But now, when I have one thin little strip, I could find another one, and I could find another one, and I could find another one. That's not showing up very well. Let's do that in the brighter red. And I could find another one, and lay them all out until eventually I found every one of these thin little strips and added them together. But notice, at that point, all I'm doing is I'm taking that area and I'm adding it with that area, that area, that area, that area. Well, now that's going along the z-axis. Now here, you notice that all of these areas are exactly the same because they're all the same little triangle. But remember, this surface doesn't have to be perfectly flat. We could have it be varying in size. So here, we wouldn't just be able to take this and multiply it times however many times because they're not always exactly the same. Oh, but we know how to add up areas of varying size. That's an integral. If you're adding up various sizes, you can do that by taking each one as its own separate size and then adding them together as an integral. So here, we're going to say we took this area, which is this, and now we're going to add those together, which is going to be another integral. Oh, okay. So now I can go ahead and write this volume as being the integral of an integral. Oh, but that's what we saw as an iterated integral. So here we can write this as the integral of an integral, which is an iterated integral. Here we would have our boundaries. Here this would be with respect to y first and then with respect to x. Now, of course, I could have done it the other way. I could have first done it with respect to x and then y. So that doesn't have to be in that orientation. But this would be the double integral, could be written as the iterated integral, first with respect to y, then with respect to x, or of course we could do it the other way around. The boundaries of integration, here, they might be constant, and in fact in mine, because my shape is so simple, I end up with constants, but they don't have to be. Remember, with a iterated integral, this would be constant with respect to this, but that does mean it could have some variable that is different than this. This could be 1 and 5, or it could be, x and x squared. Over here, these would also be constants, but with respect to both variables. So these would be constants in the traditional sense. All right? So this motivates our next theorem. This is called Fubini's theorem, and we are definitely not going to prove this one because Fubini's theorem is really very advanced and very, very long. So here we're going to simply state it and we're going to use it. This is the motivation. Here's what tells you, okay, this stands to reason. We think this should be true and we can investigate it further. The proof is a lot more involved. So theorem, and this is the theorem of Fubini. Fubini's theorem. And it states the following. First of all, we're going to start off with very little in the way of conditions. All we need is a function of two variables that is continuous on a plane region R. Let f of x comma y be a function that is continuous on a plane region R. We're going to start saying the phrase plane region. When we say plane region, we mean the xy plane. So here we have something on the xy plane. Let f of x be a function that is continuous on the plane region R. Continuity is all we're going to require here. So this is stated in two different parts. Remember I said here, from my illustration, I started with y and then with respect to x. But of course, I could have done the illustration the other way. I could have started by taking strips with respect to x first and then with respect to y. So Fubini's theorem shows us that both ways are perfectly valid, and in fact, both give you the exact same answer. So this says, if R is defined with x between a couple of constant boundaries, So let's see here. If R is defined with x bound between a couple of constants, so here we'll say a and b, and our function g1 and our function g2 of x bound our value of y, where again we will need continuity, where g1 and g2 are continuous on the interval from a to b. Then the double integral over R of f at x comma y dA can be written as the iterated integral from a to b of the integral from g1 of x to g2 of x, f of x comma y dy dx. The second part of the statement is the same as the first, but everything's flipped around a bit. If R is defined, now instead of having x bound between constants, we'll do that for y. So y is bound between c and d. And instead of having y bound between constants of x, we'll have x bound between constants of y. So we'll say this is h1 of y, and this one we'll call it h2 of y, where, and again we need continuity, this h1 and this h2 are continuous on the interval from c to d. Then the double integral over R of f of x comma y dA is equal to the integral from c to d of the integral of h1 to h2, remember these are functions of y, of f of x comma y dx dy. Notice your boundaries of integration are flipped. So Fubini's theorem shows us that a couple of things. One, it shows us that if you have this double integral, it can be expressed as an iterated integral. And it doesn't matter which iterated integral we choose. The other thing Fubini's theorem implies is that if this is equal to that, and this is equal to that, well, these two are equal to each other. But notice, these boundaries of integration, or these variables of integration, are flipped. So Fubini's theorem shows us not only how we compute a double integral as an iterated integral, but it also shows us that iterated integrals can be reversed to the opposite order of integration. So here, this shows you that as long as this is defined, well, then that's equal to this, but then that must mean this is defined, which means that your order of integration can always be flipped, which is a nice side effect of this. So after all of that, let's take a look at some examples. Example. Let's go ahead and find the volume of the solid that is given under that is under the surface given by f of x equals, let's pick a good one here. Let's do this one. Under f of x comma y is equal to 1 minus xy, like that, and which is over the region R, which is described as follows. That is between, or that is bound by the y-axis, y equals to 1, and y equals to x. It's bound by the y-axis, y equals to 1, and y equals to x. All right. So now, from our previous developments, from our previous results, we see that the volume is equal to the double integral. The volume is equal to the double integral. Okay, so that's straightforward enough to set up. Here, the volume is equal to the double integral over r of that function, 1 minus xy dA. But now, we have to evaluate this. Well, Fubini's theorem tells us that we can write this as a iterated integral. Oh, but which way do we want to write it? Well, it kind of depends on how we describe our region R. Notice, if your region R can be described with constants bounding the x value, then we describe it this way. But if we can do that describing the y value as being bound between constants, well, then we'd have to do it this way. So here, it depends on which variable we wish to do first, and that'll depend on what our region R looks like. So before we start, let's go ahead and sketch this out. Thankfully, we don't have to worry about the entire graph. We just have to worry about the region R. So let's see what that region R is going to look like. The region R is bound by the y-axis. So here's x and here's y. The y-axis is here. Y equals to 1 is over here. Y equals to 1. And x equals to y is right over here. Okay, so the stuff that's bound between the y-axis, x equals to y, and y equals to 1 is all this stuff in here. Okay, so that's going to be my region R. Well, notice I could describe this either way. I could say, oh look, this goes from a x value of 0 up to an x value of 1. Or I can describe it this way. It goes from a y value of 0 to a y value of 1. And it really doesn't make a difference. Both of those describe my region. So here, I'm just going to go ahead and pick one. Depending on what your region looks like, you might end up not caring. However, if your region was something that looked more like this, where this is curved up here, and this is curved down here, and this is flat, and this is flat, well then obviously this should be described by a constant, and this should be described by a constant. But with something that's simple like this, where there's flat sides on every side, well then we don't really worry about which way we should go. All right, so let's go ahead and describe this as an iterated integral. Notice when you write this as an iterated integral, your integrand doesn't change. It's still 1 minus x squared, 1 minus xy. But now dA is going to be written as either dx dy or dy dx. Doesn't matter which one for this particular case, but let me make the choice. All right? It doesn't matter what choice I make, but I have to make the choice. So here what I'm going to do is I'm going to choose to describe my x value as being constant. Okay, well the outer boundaries are the ones that are constant. So if I'm describing x as a constant, here I will describe the boundaries of x as constants. Then that means that the outermost integration should be with respect to x. Oh, well then that means that by default, the other one must be dy. Whichever one you're going to describe as constants goes on the outside, and so whatever's left must go on the inside. All right, and that'll be an iterated integral. Oh, but now I need to describe those boundaries. Okay, well describe your y value. The highest your y value ever gets versus the lowest it ever gets. Well, notice the highest it ever gets is always the same. It's always 1. So your upper bound is constant. But the lowest it ever gets, well, that's this line. That's not a constant. Here, the lowest y ever gets is x. All right? Y equals to x. That's the lowest you ever get to. So y equals to x. This one can only be described with constants. So the furthest left this ever goes is 0. The furthest right this ever goes, well, that's going to be 1. Right? If this is x equals to y, if y goes to 1, then so does x. These are equal. So if y goes as far as 1, then x would also go as far as 1. And there we go. We can integrate now. So let's go ahead and do that. We'll take this very first integration and do just that, which means this second integration, we're going to leave that alone for now. That's integral from 0 to 1, and we'll do that later. This part right here, let's write our dx so we don't forget. This part right here, we're going to integrate. Remember, y is the variable. So here, the integral of 1 is just y. Here, the integral of negative xy, you might think, integration by parts because it's a product. But no. Here, x is a constant. Remember, y is the variable. So negative xy, that's just a constant times y. And the antiderivative of a constant times y is that constant times y squared over 2. Just like that. Now, of course, we're going to evaluate that for y equals to x all the way up to y equals to 1. All right, that's what tells me y is equal to something. Those are my boundaries, 1 and x. And now I can simplify this by substitution. That's going to be the integral from 0 to 1. Let's see, if I plug in y is equal to 1, that's going to give me 1 minus x times 1 squared over 2. If I plug in x, that's going to give me x minus x times x squared over 2. And those are being subtracted. Plug in 1, plug in x. But now I can simplify that. That's going to be 1 squared is 1. So that's just going to be x over 2. So that's 1 minus x over 2 minus, that's just an x. And here, x squared times another x, well, that's going to give me x to the third over 2 dx. But now I can combine some like terms. Don't forget to distribute your negative. So that'll be the integral from 0 to 1 of 1. Here, minus x over 2 minus another x would be minus 3x over 2. And here, minus a minus makes that a plus x to the third over 2. Just like that. And now we have a nice simple integral. This is just the integral of a polynomial. So we can write this as the integral of 1 with respect to x, that's just x. The integral of 3x over 2, well, don't forget your minus, that's going to be 3x to the second over 4, plus the integral of x to the third over 2, well, that'll be x to the power 4 over 8. And normally I'd say plus a constant of integration, but of course here we have a definite integral, so that constant won't make any difference. And finally, we evaluate. Plugging in 1 is going to give us 1 minus, that's just 3/4, plus 1/8, minus, plugging in 0 makes all of these 0. So that's gone. And we're left with 1 minus 3/4 is 1/4. And 1/4 plus 1/8 is 3/8. So this will give us 3/8. And since you're subtracting 0, well, that's just going to stay 3/8. So there we go. The volume of the solid that is underneath the region f of x comma underneath the surface f of x comma y equals to 1 minus xy over this region has that volume. Let's take a look at another example. This one's slightly more involved, but not really. Here, the example is we want to find the volume of the region of the solid that is bound between two surfaces. So up to now, what we've done is we've said, okay, you have a surface and you have a region on the xy plane over which that surface lives. And what you want to do is you want to find the volume of the solid that is underneath there. just like that. Well, now what we want to do is we want to say something like this. We want to say, okay, you still have your surfaces, but now instead of having just one and one being on the xy plane, now you have just two completely separate surfaces. Let's say you have one over here and you have another one down here. As you guys can tell, I really, really like these kinds of shapes. Why? Because I actually know how to draw these, more or less. All right, so now what we want to do is we want to find the stuff in between here. Well, now that seems like it's a lot more complicated, but it's not. Because notice, if I find this volume here over the region R, and then separately, I find this volume here, also over the region R, this volume here is all the stuff that I don't need. All the stuff underneath that red dome is all the stuff that I don't need. Now here, if I take the volume underneath that blue dome, that gives me everything I need, but then all this extra stuff. So if I just take this extra stuff and subtract it away, all that's left is the space in between my two surfaces. But that's what I'm after. So here, the volume between the two solids, or sorry, the volume between the two surfaces is simply given by, well, we want the double integral of R. Here I'll call this top one F, and I'll call this bottom one G. Here I want the double integral of f of x comma y dA, because that's that blue one. But then I want to subtract away the double integral over the region R of g of x comma y dA. Okay. But if you go back to a previous page, you'll see that one of our properties allows us to make that nice. It's linearity. If I have a double integral of f minus a double integral of g, that's just a double integral of f minus g. So here I can stick this all together and write this as the double integral of R of the top surface minus the bottom surface. Just like that. So this isn't really any different than our previous computation. We just have to do a subtraction first. So the example for this will take one extra step, and then after that will look exactly the same as all of our other ones. So here, let's go ahead and find the volume of the solid. That is between the surfaces. Oh, let's take Z, here F, well here, let's just call them Z. Z is equal to, oh, let's see, what do we want to use? Okay, Z is equal to x squared plus y squared, and Z is equal to 18 minus x squared minus y squared. Okay, just like that. In the interest of full disclosure, I am getting some of these problems out of a textbook. I am locked out of my office currently, so I don't have the current copy of the textbook. Fortunately, I do have the homework problems, so that is up to date, but I'm currently using a several years old edition of a calculus textbook for to draw examples out of. You might see some of these examples in your textbook, or you might not. They might be problems that were assigned to you, or they might not be. I don't know. But these are the same types of problems. You know, even if this exact set of functions isn't in your problem, you'll have problems just like this, where you're finding the volume of solids between surfaces, or where you're finding the volume under surfaces, or things like that. So let's go ahead and continue. All right, well, from this, we see that we're taking a double integral, but of the difference of these two functions. All right, so now what we want to do is, remember, we have to describe our region. Okay, so we have to find where these intersect, because notice that in our illustration here, where these two were defined was our region. So having these two on their own is not sufficient. We also need to know where they're defined. Okay, so let's go ahead and find where these intersect. Okay, so the intersection of the surfaces. Remember, when you intersect two curves, you get a point. When you intersect two surfaces, you get a curve. The intersection of the surfaces. Well, that's going to be, well, z is equal to this, and z is equal to that. So let's just set this two z's equal to each other. X squared plus y squared equals to 18 minus x squared minus y squared. You can add both of these over this way. So that'll give you 2x squared plus 2y squared equals to 18. You can divide both sides by 2. That's x squared plus y squared equals to 9. And that is a circle centered at the origin of radius 3. So we know our region R. Our region R is a circle of radius 3 that's centered at the origin. Okay, so that's going to be our region. Now, we're going to take these two and we're going to subtract. We're going to take the upper one minus the lower one. You might wonder, well, how do I know which is the upper one and which is the lower one? Well, one way is we could graph these. These are surfaces. That's a paraboloid, and that is, well, that's also a paraboloid. But more simply, let's just plug in a number. We can graph these, but it might be simpler to say, well, look, these are both going to intersect here, which means that whatever they are, the upper curve and the lower curve are going to, the upper surface and the lower surface are going to cross at a circle of radius 3 above the origin. Okay, so then all the points inside of this circle are in the domain of these two functions, at least in the region that we care about. So let's just plug in a point. Let's see here. If I plug in just 0, 0, after all, 0, 0 is inside that region. 0 plus 0 is 0. Over here, 18 minus 0 is 18. Okay, so 18 is higher than 0. Okay, so that must be the upper one. So that's got to give me that my volume is equal to the double integral of R of the upper surface, that's 18 minus x squared minus y squared, minus the lower surface, which is x squared plus y squared, dA. If you prefer, you can graph these out. You could take the traces of these. That's a paraboloid. All right, that's a paraboloid. It's going to cross through the origin. 0, 0, 0 is the solution to all of these. So it crosses through the origin. That's a parabola along the xz plane. That's a parabola along the yz plane. And these would all be circles. So you would have a paraboloid whose cross sections are a bunch of circles. Like that. This is also a paraboloid. Notice that's a circle. All right. If these are if that's a constant, or that's a circle, you can move the 18 over to this side. If that traces what we're looking at, then we'd have a parabola along the xz plane, and that would be a parabola along the yz plane. Notice that the maximum value of this is at the origin. If both of these are 0, that's going to be 18. So that's a parabola that's way up here. Its maximum is at 0, 0, 18. And again, look, all of these traces, they are parabolas. But since the square term is negative, the parabola is face down. So you'd end up with something like this. And I could be even more specific by finding more values, but this gives you the idea as to what you're looking at. So here, these intersect at a circle of radius 3, and what I want is all the stuff that's in between both of those surfaces. So I want all the stuff between there and there. All right, so that's what I want. Okay, so now we can go ahead and compute this. This setup is now complete. We can write this as the double integral over r. Here, some like terms combined, make things a little bit nicer. That's 18 minus double x squared minus double y squared dA. So that's our double integral over the region R. Over here, that's your region R. So now, give this a try. Pause the video and see if you can evaluate this double integral over that region. Once you have an answer, go ahead and unpause and we'll go through it together. All right, so let's go through this together. We need to describe this region with either x as constants or y as constants. Here that's a circle, and things are about as symmetric as you could hope for. So here it doesn't really matter which way you describe them. I'm going to go ahead and describe it so that my x values are constants. So I'm going to go ahead and describe R. Okay, you say, well, that's not a flat side. Well, that's okay. Look, I can still describe this as a constant. The least x value is -3, and the greatest x value is +3. And because I'm describing that as a constant, then this volume, when I write it as an iterated integral, the outermost boundary will describe the x value. And in fact, here I can even fill that in. That's from -3 to 3. From -3 to 3. So now what I want to do is I want to describe my y values. Okay. And my y value, well, now here I have a whole lot of variable. Because here, neither the top nor the bottom is constant. This goes up higher and higher, but also lower and lower as you go along. Right? So here we have a lower curve and we have an upper curve. None of them are flat, which means both of these boundaries of integration will be variable. All right, well, that's not too bad, because notice this equation of this region is x squared plus y squared equals to 9. We had that from before. X squared plus y squared equals to 9. Now, if I want to express that in terms of y, which I do, I want to describe y, I can simply isolate y here. I can subtract the x squared over to the other side, and then take a square root. Now remember, when there's a square root, there's two values of the square root, the positive and the negative root. Just like that. But there's a positive and a negative. Oh, that must describe the upper and the lower curves of my region. So this is going to be the square root of 9 minus x squared on top, and that'll be negative the square root of 9 minus x squared on the bottom. So here, my lower bound is going to be negative square root of 9 minus x squared. That's the one on the bottom. And the upper bound is the square root of 9 minus x squared, like this. Here, my integrand should not change. So that's going to be 18 minus 2x squared minus 2y squared, just like that. So now, let's go ahead and integrate. First of all, I want to integrate this with respect to y. Here, let me rewrite that. That doesn't look very good. Let's write that as 18 minus 2x squared minus 2y squared. There we go. So now, I'm going to integrate that with respect to y. All right, so let's go ahead and take a look at this. First of all, we notice that this is an even function, and here this is symmetric. So that's going to be nice, because here we can go ahead and write that as just double the integral from 0 to that positive one. That isn't exactly groundbreaking, but it'll save us a bit of writing. So here the volume is equal to the integral from minus 3 to 3 of, here I can write that as double. In fact, let me push that to all, well, let me write that with brackets here. And I can write that as double the integral from 0 up to the positive square root of 9 minus x squared. And again, that's 18 minus 2x squared minus 2y squared. Okay. So now I can take the integral with respect to y. With one of these boundaries set equal to 0, it'll make things just ever so slightly easier to write out. So we can write this as the integral from minus 3 to 3 of double. I'm going to keep that in brackets. Double. Let's see. With respect to y, this integral is going to be 18y minus 2x squared y minus 2y to the third over 3. And that's being evaluated from 0. I should say y equals to 0, because here there's more than one place that could go. And here y equals the square root of 9 minus x squared. Okay. All right, well, obviously plugging in 0 into all of these makes this 0. So we don't have to worry about that. Here we're going to go ahead and plug in that square root. And here let me go ahead and distribute the 2 while I'm at it. So that's going to give me negative 3 to 3 of, I'm going to go ahead and distribute that 2 while I'm at it. So that's going to be 2 times 18. It's going to give me 36. And now that y is being replaced by that expression over there, 9 minus x squared. Here that's 2 times negative 2, that's minus 4. And again, that y is being replaced by that expression over there. So that's minus 4x squared, square root of 9 minus x squared, minus 2. I'm distributing the 2, so it should be minus 4 over 3. 4 over 3. Notice here that's y to the third. If you square this, that'll get rid of the square root, and then the extra y can stay put. So I can write this as 9 minus x squared times the square root of 9 minus x squared. And now all of that will be integrated with respect to x. That looks very long and complicated, and it kind of is, but we can simplify that if we notice that the square root of 9 minus x squared is a common factor. So I can now write this as, I have an integral from minus 3 up to 3. I have the square root of 9 minus x squared is a common factor. And when I factor that out, I'm left with 36 minus 4x squared minus, minus 4/3 of 9, that's minus 12. And minus 4/3 of minus x squared, that's going to be plus 4/3 x squared. All I've done is I factored that out. I factored that out, leaving me the 4x squared. I factored that out, and then here I actually multiplied those two together to give you these two. So now we're here. I note that I can simplify that expression quite a bit. I can combine some terms here. I can write this as integral from minus 3 to 3 of the square root of 9 minus x squared. Here, these are constants that go together. I can write that as 36 minus 12. I can write that as 24. And here I can take minus 4x squared and add 4/3 x squared. Let's see, negative 4 plus 4/3. That's negative 12 plus 4/3, which is negative 8/3 x squared. I can now split this into two integrals. Let me go ahead and distribute this here and here. And this will now give me, remember linearity is a nice, wonderful thing. We can split this as a difference of two integrals. So that's the integral from minus 3 to 3 of 24 times the square root of 9 minus x squared. And then here we can say minus 8/3 x squared times the square root of 9 minus x squared with respect to x. And now thanks to linearity, this can be written out as 24 times the integral from minus 3 to 3 of the square root of 9 minus x squared minus 8/3 times the integral from minus 3 to 3 of x squared square root of 9 minus x squared. Okay. Now this one, we can take a bit of a shortcut. Here we can feel very, very clever if we say, oh look, that's just the area of the upper half of a circle. Because after all, square root of 9 minus x squared, well that's, if I take the square root of 9 minus x squared is equal to y. If I were to square both sides, that would give me 9 minus x squared equals y squared. And if I added that x squared over to the other side, I would get x squared plus y squared equals to 9. So that equation gives me the circle of radius 9. Oh, sorry, the circle of radius 3. Oh yeah, but it only gives me the upper half of that circle, because here I want y to be a positive square root. So this right here, this curve is just giving me the upper half of a circle of radius 3. Oh, but look, we want to find the integral where x, and I should write that differential, where x goes from minus 3 to 3. So we want the area under this curve starting from here, going all the way to here. Well, that's just half the area of that circle. So here we can write this part as 24 times, let's see, the circle of radius 3 has area that's pi times r squared over 2. All right? Pi r squared is the area of the circle, but I'm dividing it by 2 because I want the upper half of the circle. And so that's going to give me 24 divided by 2 is 12. 3 squared is 9. 12 times 9 is 108 times pi. 108 pi minus, this one is, well, unfortunately a lot more complicated. This one does require us to use trigonometric substitution. I think, let's see here. Let's write this down first. Oh, I changed my 8 into a 1 for some reason. There we go. So that is our integral. And let's see, I believe this requires integration by trig substitution. And in fact, here it is. It is a bit of a long computation. I've gone ahead and written it out. That way it flows a little smoother. In the interest of disclosure here, if this took you a little while, well, it took me a little while too. This took me about a little over 10 minutes to go through. So here, we've already done this part. And here we've done this part here. So all we're looking for is this number there. So that's going to be 108 pi minus 8/3 times, and then we're going to evaluate this thing right there. All right, so here we have, you use trig substitution. Here, this is an even function over a symmetric set of boundaries, so we can just double from 0 to 3. Here I'm going to take x equals to 3 sine of u as my substitution. Notice that means that u is equal to the sine inverse of x over 3. You can solve for u here. And if that's equal to x, well then that's dx. So now this x becomes 3 sine of u quantity squared, square root of 9 minus, and then again the x becomes 3 sine of u quantity squared. dx, well that's going to be 3 cosine of u du. Don't forget your differential. But now I've changed my variables of integration, which means I should also change my boundaries. Notice here, if x is equal to 0, well I can plug that in right there. U would equal to the sine inverse of 0, which is 0. So my lower bound can stay 0. I don't know if you can tell, but there's some white out there because I actually forgot to do this when I first started to do it. And I was right around this step when I realized, oh, I need to change my boundaries as well. Here, if x is equal to 3, well, I've changed things from 3 to u. So here, if x is equal to 3, I can plug it in right there. And u is equal to the sine inverse of 3 over 3. The sine inverse of 1. Well, that's pi over 2. Okay, so my bounds are now from 0 to pi over 2. This will save us a lot of trouble at the end because as long as this is, imagine if you were to get to this point and then you would have to back substitute to get you back up to x. Instead of having to back substitute, at this point, you just plug in those new boundaries, which makes things much, much faster. This is really about just over half the work that it would require if we didn't change those boundaries. So now, the boundaries are different. Here I've squared this and I've squared this. 3 sine of u gets squared to give me 9 sine squared of u. And now the Pythagorean identity, 9 minus 9 sine squared of u, is 9 cosine squared of u. But since that is now a perfect square, I can take its square root. Notice nothing else is changing so far. These are all staying the same. I'm only working here. The square root of 9 cosine squared of u is 3 cosine of u from here to here. Well, now these are all constants, which I can go ahead and factor out. 9 times 3 is 27, times 3 is 81. And if I pull my 81 all the way out here, well, there's already a 2. 2 times 81 is 162. And that leaves me sine squared of u. And I have a cosine of u and another cosine of u to give me cosine squared of u. Just like that. Now, I have the integral of the squares of sine and cosine. I'll use the power reducing formulas. We're really using our Cal 2 today. Our power reduction formulas, sine squared of u is 1 minus cosine of 2u over 2. Important thing is here, you reduce the power by doubling the argument. Same thing for cosine. It's almost exactly the same, except sine has a power reducing formula of minus right here. Cosine's power reducing formula has a plus right here. Otherwise, they are the same. Here, the 2 times the 2 is a 4. So I can factor out a 1/4 out here. And let me just leave my numerators. If I multiply out my numerators, that's going to give me 1 minus cosine squared of 2u. Okay, so multiply these two together, that gives you this. So now, right here, that's still an even power of cosine. So I'm going to use the power reducing formula again. I'm going to leave that 1 alone. That minus I'm going to leave alone. But now cosine squared of an argument is the same as 1 plus cosine of double the argument over 2. It's the same as this formula. Notice that argument was already doubled. So we're doubling it again, and that'll give us 4u. Here I just went ahead and reduced the fraction. Now, I notice I can factor out 1/2 from here. So I can take the extra 1/2, pull it out. So that joins the outside, gives me 81 over 2 divided by 2. That'll give me 81 over 4. And now, if I factor out a 2, this becomes the number 2 minus the number 1, which is 1. And then I can distribute this negative to give me negative cosine of 4u. Here, if you gave these a common denominator, you would combine. This would be your numerator, and that 2 I just pulled to the outside into my denominator. And now this is nice. I can integrate this. With respect to u, that's, well, the integral is just u. Here, the integral of minus cosine of 4u, well, that'll be minus sine of 4u. Oh yeah, but the chain rule says I have to now divide by the derivative of this. So that's going to be 1/4 sine of 4u. And finally, we can plug in our endpoints. We have 81 over 4. And then all of this is being multiplied by that 81 over 4. Okay, so if we plug in pi over 2, that's pi over 2 there. That's pi over 2 there. And then separately, I could plug in 0 there and plug in 0 there. Well, notice, sine of 4 pi over 2, sine of 2 pi, that's 0. So this part goes away. That whole thing is 0. That's a 0. And here, 4 times 0 is 0. And the sine of 0 is also 0. So all of these go away, and you're just left with pi over 2. So that's going to give you 81 over 4 times pi over 2. 81 pi over 8. And that's the number we wanted. That 81 pi over 8 is the integral from negative 3 to 3 of x squared times square root of 9 minus x squared dx. So 81 pi over 8 is that number right there. 81 pi over 8. This will give us 108 pi minus, here these two 8's can cancel out. This gives me 81 pi over 3. And finally, I can combine my like terms. I can give these a common denominator. Oh, let's see here. 3 and 3, like that. And so that would give me 324 over 3, and that's times pi, minus 81 over 3, and that's also times pi. And if I subtract those, I get 243 pi over 3. Oh, I can actually divide that, can't I? If I take 243 pi over 3, I can divide those numbers, and that'll give me, oh, what would that be? I can do all that other stuff, but I can't do division, right? That'll be 81. And that will give me 81 pi. So the final result is, if you're going to take the, let's see, where was the first page of that? If we wanted to find the volume of the solid between these two surfaces, here was our setup. That gave us this region, which gave us this double integral. All right, it gave us this iterated integral. We evaluated the first part of the iterated integral. That wasn't much of a problem. It was a couple of short steps. But then when we got to the second part of the iterated integral, the integral with respect to x, that took a bit of effort. This first part, we did it by being exceptionally clever and saying, oh yeah, that's the upper half of a circle. If we hadn't been exceptionally clever, we could have done this by trig substitution also. But here, this was much shorter if you notice the geometry of this. But this one, well, at least I didn't notice any nice geometry on this one. So here we ended up with a rather long computation that involved trig substitution, which looked like this. But from that substitution, we get 81 pi over 8, which goes in there, and that gives us our final result. Right. So that is it for that problem. That was exceptionally long, and we got a good use out of our Cal 2 today, along with our Cal 1 and maybe a little basic geometry, which is why I chose this problem, and in spite of the fact that it is, well, it was just as long for me as it was for you. So that's the end of the section, and the and the homework is as follows here. The homework for section 14.2. Go ahead and try problems 7 through 39 odd. I hope you all have a nice day. If you have any questions, please let me know, and I will see you later.